Okay, so let's get into some use cases. So this is, one of the first things that we brought out with 60 East, which is, Jeff Birnbaum's company. Amazing guy, really bright software architects. They're all about pushing the limit of low latency, high performance messaging. It's all about throughput at the absolute lowest latency. And so, what you have on the left is basically a mixed workload where you're doing, maximum transfers of sequential writes, but doing random read back for real-time analytics. It isn't only writes, it's actually reads mixed in with the writes. And there's two, and don't forget here on the left, this is a logarithmic scale also. From here to here is an order of magnitude. So you have to focus on the consistency of the performance, the latency that you're getting, combined with the throughput. And actually, I kind of jumped over, one of the key slides at the beginning, but really what we try to do is get the throughput and the latency at the same time. That's what people struggle with, right? They might say, hey, I can get 4 gigabytes or 8 gigabytes, but how long does it really take each I/O transaction to complete? Somebody mentioned spinning disk, you can get, gigabytes per second. True. What's the actual latency? You're only talking about throughput. Talk about both at the same time, right? That's the key. And frankly, that's what the application will end up consuming, right? It needs, that's why memory is so important. It gives you latency and bandwidth simultaneously. And that's what this architecture does. So what you tend to see is a significantly lower latency, very consistent, and factors of acceleration in the actual throughput of itself.
That's a PCIe SSD card that you're comparing against, is that?
So this is, yes, so this is, okay, so 60 East was tuned on the Fusion platform using their file system. Essentially, this is what the application had been tuned on leading up to us. All they did was take out the card, replace it with MCS, and got, bang, this level of acceleration. No changes. It was literally move it from one storage media to the other and just rerun the exact same thing. Okay? So you're talking here about 2 gigabyte per second publish rate. So we're achieving writes of 2 gigabyte per second at a latency 29 microseconds. This data is actually old. We're significantly better than that now. So you can imagine we hit close to 3 gigabyte at 20 microseconds. So we have a 50% improvement over even what we're publishing now, even in the latency. These numbers were done probably 6-7 months ago, and they had no optimization whatsoever. The slide is a little older, but you're still talking about 5x the throughput at essentially 5x the latency. It's almost becoming an order of magnitude.
What do you attribute the 99.9 percentile write latency difference to? The last columns there.
The flash management, the FTL.
Yeah, so you've got superior flash management and SanDisk that's helping you.
Remember I talked about the distributed FTL.
Right.
The minute you stress the FTL, you're going to see these spikes.
Yeah.
Okay, so you can only get the consistent performance if the garbage collection and things like that are not getting in the way. Now, it's difficult to hide that at these rates, right? But you could also do something else. You can throttle the performance, and then you're going to get very consistent, or you can go as fast as you can. People manage it in different ways. Here, we're actually writing as fast as we can, and it's very consistent. The reality is, it's all about the FTL when it comes to writes, and the ability to commit the data very early. Yeah. And that's why the write performance is so disruptive. Okay? This is a very interesting application. So this is using mmap. So the way this test worked was, I'm not sure if people are familiar with memory mapped.io, but you basically say, okay, I'm going to map a file into a range of memory. And anytime a page doesn't exist in memory, I'm going to page it in from the file and then use it. okay? Anytime I want to persist something, I essentially say, you know, sync it, and then that page will end up getting written out. This is using what is there today in the Linux kernel, which, by the way, is extremely slow. Right? It was never designed to handle something that can persist at the rate that we can persist. So obviously, this is one of the things going forward that we're going to take this, throw it out, and replace it with something that can persist not only pages, because this is optimized for pages, but also cache lines. That's what I was talking about before. But using what we have today, so here you have microseconds. So what we did is you basically make sure that everything is mapped into the 20 gig range. This was done by a third party, wasn't done by Diablo. And what you can see in red is the latency at which the data is being persisted. And you can see the 99.9999 percentile of outlier transactions. Okay, so what this is saying is that if I have a file that's memory mapped, and I'm essentially running it almost like an in-memory database, I will get at least 3x more throughput at lower latency with orders of magnitude more consistency compared to the other solutions that we're testing. And one of these solutions was a 34 nanometer SLC card. So again, comparing 19 nanometer MLC NAND with 24 and 34 nanometer MLC and SLC. Okay? Obviously, the performance here is coming from the parallelism, the flash management, and this is the type of stuff that the guys on Wall Street are very excited about, right? This is essentially an in-memory database that's paging data in and out when they get a page fault.
This is a logarithmic scale, another thing.
Yeah, this is logarithmic here.
And this is synchronous sync, which is...
Yeah. That means a write blocks everything. So your ability to persist the data is actually going to block the transaction rate. So this is synchronous. It's a good point. Yeah. Yeah.
This is using the SanDisk card? Is that?
This is done on UltraDIMM. All of these measurements are done with the product. Now, in some cases, they were done on early. Now, the firmware gets tuned. Like, for example, we're adding stuff in our firmware that leverages and takes advantage of their performance, and it gets tuned and better. But basically, this is all done on the SanDisk media. Okay, really exciting one for us was the work that we did with Percona. Starting now to move away from, top of the pyramid and starting to move into the body of the pyramid. When you get into MySQL databases, you're talking now about a huge market, and also a market that's applicable to any relational type database, including Oracle, DB2, and others, SQL Server also. So what we did is we went out and partnered with them and said, okay, listen, we're going to set up some servers, and we want you to get on the servers and just test them and see how we perform compared to other solutions. And if we perform better, okay, what can we do next then to get even more performance out of the solution? But the first step was to say, okay, do we have any value here at all? Okay? So they basically got some systems. We gave them the systems. They were accessing them remotely, but they were driving everything. And they ran a lot of things, but some of the results I'll give you are SysBench benchmarks, which is essentially an I/O generator, and LinkBench, which is actually a load that's driving a real MySQL database. So this would represent what it would look like for a user actually using MySQL. Okay, and we got a whole bunch of metrics, and I just want to point out a couple of the speeds and feeds here. Okay, so this is throughput in megabytes per second. Okay, so obviously you want to be as high as possible on the graph. Okay, and this is threads, and the font is not the right size here, but this is one thread, two, and then a binary increment all the way up to 1024. Okay, so every one of these ticks is basically a binary increment. Mm-hmm. Now, this is the most important part. Look at the single thread performance on the writes. Okay, so in this case, it's 250 megabytes. This is an 800 gig configuration. This is a 1.6 terabyte configuration. Okay, and this is a 1 terabyte card. This is a Fusion IO
It's a
card.
log scale. That at one is like almost like 100 or something like that. It's not even 250.
No, this is linear. It's 500 and 1,000.
Oh, okay. All
It's
right.
250. I could have said yes, it's logarithmic, but it's not.
Yeah,
It's
thank you.
250. Okay,
better.
but we don't have to mess with the numbers for this to look good.
Yesterday was
So 250 on one thread. But what number would they tell you? They would give you this one,
this one.
right? They would say our write throughput is 700 or 400 megabytes. Now, in actual fact, the application is actually going to see this.
Yeah.
In our case, with one thread, we can actually achieve the maximum throughput. So when we say we can get 600 megabytes, the application can actually get 600 megabytes. Now, this is also interesting. You add 4 more devices, perfect linear scaling. Hey, what happened here? The application thread is the bottleneck here. In amps with 60 East, with one thread, they actually max out the subsystem. And you will see that actually they can get almost 2 gigabyte per second, one thread. Amazing, okay? That means this is sysbench, right? Unmodified. Obviously, the 60 East guys are tuning. That's their game, okay? But sysbench unmodified, single thread, look at the difference in performance. Now you're talking literally about 3-4x the throughput single thread. That's what the application is going to see. So let's keep going. So I have this thing where I say, not all 1 million IOPS are alike. People throw out numbers. They're meaningless. You have to really look at what is the application going to see, what is it going to experience. Nobody talks about this. They only give you this number. And then even you can see there's spurious dots all over the place. We have those dots, but they're up. They're not down. So let's keep going. So these are reads. So we talked before about, hey, anybody, what about the reads? You're limited in bandwidth. Okay, well, this is a 25 channel device. There's 25 flash channels here. It's pretty big. Okay, so they're able to get at a queue depth of 64, really at a queue depth of 32, they max out their read bandwidth at, let's round it up to 1.5 gigabytes. Here's the interesting part. At the same queue depth of 32, we're getting essentially 30% more throughput, okay? At a queue depth of 64, you have 2 gigabyte per second. Now, most people will give you this number and say, hey, that's our throughput. At 8 devices, at a queue depth of 64, we're delivering 3 gigabyte per second, the same queue depth. What does that mean? It means that the average latency per transaction is substantially lower.
Riccardo,
That's real work that's being done by the thread.
So the first graph there, the UltraDIMM 4, is actually 4 UltraDIMM slots?
Yes,
Okay.
4. And this is
Versus
8.
one PCIe card, right? Of 800 gig or something.
Yeah, but this is a 4 times 200 configuration.
Yeah.
Now, what I'm showing, the real comparison on a gigabyte basis is these two. Here, what I'm trying to show is the scaling effect that you get. Okay? And that's the important piece. This is the true performance comparison, where essentially what we're saying is at a queue depth of 64, we're doing 2 gig, compared to at a queue depth of 64, at essentially double the latency here, you're getting a 30% increase. But what I was trying to highlight is look at the scaling that you get as you start increasing in parallelism. Trying to drive home the message, parallelism is where performance comes from. Okay? And this translates into real work done by the application. Let's keep going. Now, mixed workload. These are writes, these are reads. You have to add them to get the total number. The exact same story. When you add up the work that's done at a queue depth of 64, you're talking about almost a gigabyte of throughput on a mixed workload compared to essentially 500 megabytes. Twice the performance, at half the queue depth. That translates into work and latency. So let's see what this means for the link bench MySQL load. This is pretty amazing. So what this is showing is that in the 4 DIMM case and in the 8 DIMM case, this is the Fusion card. So the ones that you want to compare from a capacity perspective are this one and this one. What this is showing is this is the amount of transactions per second that have been executed by the database in the same snapshot of time. Okay? So this is low on the axis and is essentially stopping at, short of 5,000. We are basically doing about 5 times more work, 5 times more transactions per second, the exact same capacity of NAND, same database load. The work executes 5 times faster. So this is showing efficiency at the application level. Another way to look at it is I/O throughput. I/O throughput is essentially transactions. That's what a database is doing.
So the three graphs that you're showing are 3 separate benchmarks? Is that what you're?
This is the same benchmark that's run on a Fusion card.
No. I mean the vertical graphs. There are 3 separate graphs here you're showing vertically.
Yes.
What's not showing actually, it's for
the first
different
one
buffer
is-
pool.
Different buffer pool size.
24 gig
6, 12, 24.
Threads?
buffer
pool.
pool.
Buffer pools.
Yeah.
So we're varying the amount of RAM.
Okay, I got
Yeah,
you.
you want the buffer pool to be smaller because the amount of RAM that you need to get the same performance is smaller. This is showing that see here, they vary the buffer pool. As the buffer pool gets bigger, they do more work because they're essentially taking advantage of more RAM.
Mm-hmm.
What we do is we can crush the amount of RAM down by a factor of 3 and still do essentially almost 3 times more work. So this is actually showing that you could offset the amount of RAM you have in the system by having a massively fast storage subsystem.
Right.
The reason for that is because we are essentially eliminating the bottleneck, and it's all now the CPU is the bottleneck, which I'm going to show in 2 slides.
Right.
So you actually raised a good point. This is showing that we do not need RAM to accelerate the application, which we leverage very extensively in virtualization, by the way. But here, you can see that the reason it's getting faster is because they're increasing from 6 gig buffer pool to 24 gig buffer pool.
Yep. And mind you, it's not getting that much faster.
Well, you can see it improving,
Percentage-wise.
but I mean, relative to us, of course, the numbers look small. So this is actually throughput. You can actually see that the throughput is, not changing by that much, to your point. It's the same thing for us. But add up the numbers, you can see that this, from a throughput perspective, now you can actually tell on the actual graph scale that we're literally, 3 to 5 times more throughput. Same workload, same server, everything done by Percona, completely independent of Diablo. Okay, now here's the big thing. When they graphed CPU utilization, in our case, the CPUs were pinned completely to the hilt. This machine was doing as much work as it could, which means more CPU cores, faster CPUs will produce more work. Isn't that what removing the I/O bottleneck is about? Mm-hmm. In this case, adding more CPUs would have done nothing. This was I/O bound 100%. Okay, and actually adding the RAM, what is that doing? It's allowing the CPU to cache more I/O in the RAM. That proves that the application was I/O bound. And so really, this is what we talk about in terms of work done per gigabyte of flash that you add. This is how we want to disrupt the data center with this technology. Okay, last thing before we open it up to questions, virtualization. What we're trying to do here with virtualization is essentially create an architecture where, imagine everything is distributed, right? So Diablo is all about distribution. So what we're looking to do is create a very high performance, cost effective persistence tier that's spread out across the network. Okay? And a caching software or a storage software that does replication, what is it trying to do? It's saying, okay, if you want to write your data, I need to write it to several different places before I can say it's actually done. Because it needs to be redundant. Our write performance becomes very important to the application. And somebody mentioned RDMA. Well, think about, if you combined RDMA with our level of persistence, how you could accelerate a distributed storage type application. And that's essentially what we're talking about. Not all flash is created the same, right? You don't need the entire flash that's in a subsystem to have the same level of performance, the same type of cost. So what we're looking to drive, right, is a concept where you take advantage of the reduced latency in the stack and create a low latency, high performance persistence tier that you can essentially combine to get more scalability, more performance per virtual machine, and overall lower cost. Okay, and what the architecture looks like is like this. Imagine you have a two-tier structure in every server with the dense tier being very low cost. Can be a disk, can be a SanDisk cloud speed, ATA drive. There's no reason for it to be high performance. It's just interesting to have the bulk storage here. The persistence tier that's giving you the performance is actually the MCS tier. And so what you have in every server is you have processors, RAM, the network, the low latency persistence tier, and then the bulk storage. And so our next foray into acceleration, which we're going to be announcing results in the next couple of months, is going to be in this area where people are essentially saying, okay, I'm going to create a server and I'm going to scale it out. It's like a Nutanix or a lot of these guys that are doing distributed file systems, distributed storage. That's the direction that storage is essentially going to, disaggregate and scalable. So now you create this concept of, no, I don't want to use 400 gigabytes of RAM to get the performance. You can use 400 to 800 gigabytes of low cost, dense flash, persistent media that's replicated across the storage area network that is essentially running on the network. So in the next few months, we're going to be rolling out performance numbers around this type of architecture. And now you're not talking about a niche. You're talking about IT infrastructure in the virtualization world, which is 75% of the server industry. But not all flash needs to be the same. Not all endurance needs to be the same. Not all performance needs to be the same. And so this is, essentially not an attack, but it's how we envision the all-flash storage array being. It's distributed across low-cost servers, very scalable, and it performs like stink, but it's very cost-effective. So look, in summary, we think memory channel storage is only at the beginning of the impact that it's going to have on the industry. Obviously, if you change nothing in the operating system and the application, you can see huge benefits. Now start thinking about when people start natively taking advantage of this at the operating system level, hypervisor, application. And now think about us learning as we go along, thinking about all the things now that we can do, now that we've learned what the applications are really trying to do. That's called evolution, it's called improvement, it's called continuing to evolve the technology. And that's what we're going to be doing. So for us, we're amazingly excited about where we're at today. And obviously the focus is to execute on growing the business, for SanDisk's benefit, my investors, everybody, right? But we also are not losing sight of the fact that people are working hard to catch us. And we're working hard to stay ahead. And the team is all about winning, right? We're all about being dominant. We don't want to be anywhere near anybody in performance. We want to always have a very clear delineation. Now the question is, how do we actually translate that into a cluster that's deployed, 1,000 machines at a time? Well, that's our goal, to drive this into the mainstream and monetize it, right, for everybody's benefit, in particular our investors, our customers, our partners, to the benefit of the user. But I think the message here is we have something amazing today. but it's not going to stand still, right? There's a lot of room here for us to evolve it, and we're excited, and hopefully so is the industry. So that's it for today. Open it up to questions.
Can someone,
What, no applause? Come on.
You asked for questions.
Wait a
Yet,
second. And we made
no applause.
and we made the man beg
can,
And sorry?
can someone,
for the applause.
Justin wants to ask a question.
yeah, just,
Yeah.
can someone remind me why we're not using memory channel to access persistent storage in the first place?
Ooh, that's a really good question.
Persistent storage meaning what? The flash, the NAND?
Anything other than DRAM? Like, I mean, the reason...
Essentially, why didn't somebody do this before? Like, why didn't?
Isn't there a SCSI controller hung
we
off of
we
this
used
thing?
to have persistent RAM, yeah. As Howard was tweeting before, you could reboot a PDP-8 and it would just come back up. But
It wasn't reboot; it was just power on.
we just power it off and then power it back on. It didn't actually clear RAM because we put in DRAM because RAM needed to
was
be
cheap.
dynamically refreshed because it's cheaper.
Well, and
Get
faster.
more than and faster than just core.
Well, no, SRAM is
So-
faster than DRAM,
Yeah.
Yeah.
But it's not as dense.
but it's all
And more
The
expensive.
value of
We went- we
DRAM
went
is
to-
that little
we went to
capacitor can
DRAM
be scaled, right?
because it's cheap,
Yeah.
Yeah.
So we,
And it's denser than SRAM.
But don't forget the
which makes it cheap.
don't forget the focus
Yeah,
of
no, of
Justin's
course.
question. Why aren't we hanging other things off of this thing?
Yeah.
yeah, why did we go
Okay,
with
well,
an
I'll tell you this. Our prototype, our initial prototype, had an ATA connector, a USB connector, an Ethernet connector. We built a protocol here that is completely abstracted. And in fact, we actually proved that it all worked. In the end, once, the secret sauce is that tunnel that Maher talked about, where once you can deterministically get all your zeros on the other side, then there's no limit to what you can do on the other side. Now, what's the practical application of that is a different story. Here, we're focusing on something very practical. But if you ask the question, why can't I do Ethernet on the other side? Well, of course you can. It's already been done in the prototypes in our labs, right? The question is, have I thought about, or has he thought about where I can actually use Ethernet
The question then becomes: is doing Ethernet off of
any value, right?
off of that DIMM any better than doing Ethernet off
exactly.
of PCIe?
And what do we lose doing that?
Right.
Yeah.
So, but those are two different questions. The question is, can you do it? Yes.
Yeah.
In fact, we've proven
Should you
can.
do it? No.
Should you do it? Is there a market? That's a business. Here we understand why we want to do it.
Yeah, this is a very clear use.
But let's be clear. It is a platform, right? That you can essentially. Now, if you say, hey, what about not flash? What about some other non-volatile media?
Right. Well, as we start talking about
that
when we start
becomes
talking about
interesting.
PCM or
Exactly.
spin torque or memories that are non-volatile but less weird than flash.
Yeah.
Then
And that's why we're careful
10
to
years
call
from
it,
now, things get really interesting.
Exactly. And
But
that's why we
the
call
real,
it a
the real answer to your
non-volatile
question,
media.
Justin, is the semiconductor guys drove it.
Yeah.
That we didn't until flash became cheap enough to do this with. There was no non-volatile medium that made any sense.
Yeah.
It would have been an Edsel.
Well, it's interesting, isn't it, that essentially each element in the data center had their own skin in the game and made their own bus or channel. And so the semiconductor guys had their memory channel, and the storage guys got our fiber channel, and the Ethernet guys, and the and
Don't go
the
to Ether
PCI
channel because then
people,
we'll have to
and
pay Cisco royalties.
and now a lot of people are talking about convergence on PCI. But basically, TLDR, why are we converging on PCI when we've got this other useful channel that we could use that's maybe even better for certain applications?
Data access, it's significantly better.
Yeah, for some applications. And I think that's the other thing too. We have to admit that memory channel is really not ideal for like USB, right?
No, and
I mean that would be stupid.
exactly.
No, and there's
Would.
and there's severe distance limitations to memory channel that we made the transition. Everything outside the box and even PCIe is serial
Yep.
because very high speed parallel over a distance longer than about this
It's hard.
is almost impossible.
Oh,
and so
I think is impossible. It's
Yeah.
3-4 inches, yeah, for sure.
and so
I wanna
No matter what you're talking about, there are trade-offs.
Right.
And we've got, questions of hot plug and portability and space and power and cooling. There's all sorts of reasons that you wouldn't use this for Like, I was joking last night that you guys are going to come out with a disk drive that plugs into a memory slot, because wouldn't that be hilarious? But, you know, I mean, there's all sorts of reasons you wouldn't do that. And it doesn't
basically what it
necessarily
is.
just boil down to latency
I-
or distance. It
I
boils
could
down
see
to all
fitting the
sorts of
little
things.
air shield over the disk drive as being an issue too.
Now, all jokes aside, I do want to add one more thing to answer really a question about why is it difficult. So somebody says, hey, why can't you just talk to the flash? Well, if we go back to the media management, the thing about DRAM is that when you write to it and read from it, there's no translation layer, right? You write the bits, you read the bits. That does not exist in Flash, right? Nobody except the media management layer of a chip talks to the NAND. Everything is abstracted because you can't reliably even read from the NAND without there being errors, right? I think everybody understands.
Right, there's error rates, there's that you have to write blocks and erase pages, and it's
Exactly.
It's
So
just,
this
it's too
is-
weird to do that.
This is all about creating tiers that allow you to get the accessibility and performance while taking into account the fact that the media, you know, everybody talks about, hey, Intel's going to come out with a processor that talks directly to NAND. Why would they do that? How could they do that? Right? They have that. That's called PCIe. The reality is, you have to think about the NAND is so far away. There's a million things between you and the NAND that have to be taken into account. You can't actually access it directly. And the same thing will be for Torque RAM, PCM, you know, anything that is not DRAM needs a media management. And that's why MCS is really interesting for that, because you can actually abstract the media management and get the performance. You know, something like PCM, I don't know if it'll win, but you know, you write to it in microseconds, you read from it in 100 nanoseconds. Think about combining it with MCS. We could absorb the writes instantly and deliver the reads instantly, and all of a sudden combining it with MCS will give you DRAM-like performance. Is it as dense as DRAM? You know, what's the power? We'll see which one wins, but combining it with something like this is the only way to make it practical and usable.
That would be the equivalent of putting Flash in front of a server today. We're just moving it into the silicon right next to the server.
Yeah, it would be equivalent to making the DRAM persistent, because something like Torque RAM or PCM is not anywhere near as dense as Flash. It's about the same density as DRAM, but it's persistent.
Ooh, hybrid memory.
Hybrid memory.